Okay, hello everyone. So today our speaker will be Anupam Datta, and his talk will be on Atiyah's paper on algebraic topology and operators in Hilbert spaces.
Yeah, thank you very much for the introduction. So today I'm going to be talking on one of Atiyah's many papers where he links how you can prove Bott periodicity by methods which do not necessarily stem from pure algebraic topology. And this is one such paper where he uses methods from functional analysis. And maybe a couple of remarks as to why I went after this paper. Number one is that I had already studied it a bit in the past, and I think there are some nice ideas which Atiyah has tried to convey here, and I thought it would be good to share this with audience who have seen more homotopy theory. And second of all, I think there are some things which probably could have been done in a much more cleaner way, and some of the technicalities which I had fixed once. And again, I thought it would be a good thing to share it with you all. So without further ado, let's see what we are going to do today. Firstly, I will be defining what compact and Fredholm operators are on a Hilbert space. And then I will be defining a nice class of Fredholm operators known as the Toplitz's operators, and prove a theorem known as the Toplitz's index theorem, which in some sense is an extremely baby case of the Atiyah-Singer index theorem. And finally, I will sketch a proof of complex Bott periodicity using these ideas which predominantly stem from functional analysis. And time permitting, I will also discuss some results on the homotopy groups of the space of Fredholm operators on a Hilbert space. Okay. So here's the setup. For me, every space that I am, or every Hilbert space that I am going to talk about will be infinite dimensional separable and over the complex numbers. And inside that, we want to look at a certain subclass of operators or bounded operators from H to itself. And in particular, we have that the bounded operator is called compact if it sends the unit ball of the Hilbert space to a pre-compact set, meaning whose closure is compact. And these classes of operators are really nice in the sense that, well, probably some examples will help us to get a better feeling of it. So first of all, note that if your operator has finite rank, then it is automatically compact because you are landing into a finite dimensional vector space, and we know that closed and bounded sets therein are compact. Second of all, here's example of an operator which is not of finite rank, but is still compact. And the reason being is that when you take the standard orthonormal basis EI and you divide it by I as n gets larger and larger, this thing will get extremely small, and you can do some basic analysis and conclude that this is indeed compact. And we want to study the space of compact operators, which I will be denoting as K of H. And the point is that it is closed. This is again an elementary fact from function analysis, but it is in fact also a two-sided star-closed ideal in B of H, which may not be immediate from the definition, but if you sit and observe how the composition of two operators are defined in a Hilbert space, and note that if you land in a compact space, then the image of that is also going to be compact. You can easily verify the properties of it being ideal. And by star closed, I mean that the adjoint of a compact operator is also compact. But the most important property for K of H, or at least the one which I like the most, is that it is the unique proper closed two-sided ideal in B of H, where H is separable and infinite dimensional. And this is kind of interesting because if you take any closed ideal in your space of bounded operators, which is non-zero, then sure, it contains finite rank operators that you can easily check by just multiplying it by a projection onto a finite dimensional subspace. And if you have all the finite rank operators, you will also you can take their closure. And the point is that this closure is exactly K of H. So K of H is, you can equivalently define it as the closure of the ideal of finite rank operators. And in particular, this gives the proof of 3. Okay, so this was all for compact operators. And now I want to discuss another nice class of operators which are called Fredholm, and these are the ones which will play a central role in our proof of Bott periodicity. So we will call operator Fredholm if its image is closed in H, and both the kernel and the co-kernel are finite dimensional. And in this scenario, we will define the index of our operator to be the difference between the dimension of its kernel and the dimension of its co-kernel. And note that, I mean, this makes sense because we are assuming both the kernel and co-kernel to be finite dimensional. So index of a Fredholm operator is going to be an integer. And again, we have some basic facts about them. So the right shift operator, which takes your orthonormal vectors EI to EI plus 1, is a Fredholm operator, and you can check that its index is -1. Why? Because the right shift operator is going to be injective, but when you look at its co-kernel, then you can see that you are always having a 0 in the beginning, and when you quotient that space, it precisely has dimension 1, and so this difference is going to be -1. Another basic fact from function analysis is that the space of Fredholm operators is open in the space of all bounded operators, and moreover, the index map, which takes a Fredholm operator and assigns to it its index, it's a continuous map. And yeah, this again is some basic function analysis, but I kind of like the spirit in which you can try and prove it, in the sense that if you recall the winding number of, if you have a point in R2, and if you have a simple closed curve, you can try and define, like a closed curve which does not contain that point, you can try and define its winding number, and there also you have this kind of locally constant things coming up. And I personally feel that the flavor here is kind of similar. Yeah, and the next property is that if you take two Fredholm operators and then you take their product, or like product in B of H, which is just composition, then the index of the product is nothing but the sum of their indices. And this in particular shows that the space of Fredholm operators is a H space with this multiplication. Yeah, it's the multiplication is going to be continuous because you are in B of H. And now we have a pretty nice theorem. So you might be wondering that why I talked about compact operators and then Fredholm operators, and apparently these two classes of operators are not that related. But the answer is they are very intimately related, as the following two results show. So for one direction, you have that if you have a Fredholm operator, then you can always find two bounded linear operators, G1 and G0 and G1, such that FG0 minus the identity and G1F minus the identity, these are compact. And moreover, you can just take the difference of G0 minus G1 and play with it, and you can obtain that you can, in fact, take this G0 and G1 to be the same operators. And the beautiful part is that the converse to this result, which should be 3, I don't know why I have written 2. The converse to this result also holds, and this is known as Atkinson's theorem. So Atkinson's theorem essentially tells us that an operator is Fredholm if and only if it is invertible modulo compact operators. Or if you were from a more C-star algebra background, you can take your C-star algebra B of H, and then you can quotient by the ideal of compact operators. This is again going to be a C-star algebra. And therein you can look at all the elements which are non-zero. And then the class of all those elements inside your B of H, that is going to be Fredholm operators. Yeah. And this Atkinson's theorem also has some nice corollaries, which are something like, first of all, if you have a Fredholm operator, then its adjoint is also a Freedom operator, and moreover, the index of F star is negative of the index of F. This kind of follows immediately from this equation, because if you have this and then if you take adjoint on all the sides, then, well, adjoint of a compact operator is a compact operator. And yeah, I guess you can take it from there. But this is really trivial after you have Atkinson's theorem. And now let's try and understand how paths in the space of Freedom operators look like. Because at the end of the day, we are going to study some topological properties of this space, which in turn is going to be helpful to us later. And to that end, we have this little result that if we have a Freedom operator and if K is a compact operator, then the sum is a Freedom operator, and the index of the sum is same as the index of the original Freedom operator. The proof again is just straight up from Atkinson. So I wouldn't say much, but the point is, if you directly plug in and check all these equations, you will get that Atkinson's theorem indeed implies that F plus K is going to be a Freedom operator. And for the fact that the index remains invariant under the perturbation by a compact operator, just note that you have a continuous part in the space of Freedom operators where you take T to F plus T times K. And the point is, you indeed land in F of H because, well, if K is compact, then T times K is also going to be compact. And then I just showed previously that sum of a Freedom and the compact operator is the Freedom operator. So this is a legit part in F of H. And now you push forward this thing with the index and you land in the integers. And as the index was also said to be continuous, the composition is going to be continuous, and you get that these two things are the same. But now just it's trivial that gamma of 0 is F and gamma of 1 is F plus K. Right, but if you think more carefully about this proof, what I essentially showed was that if you have a continuous part in F of H, then the index of the starting point is same as the index of the ending point. And this somehow tries to give a hint towards what the part components of F of H could be, or in other words, we can try and guess how we can try think about pi naught of F, the space of part components. And to this end, we have a result which says that if you take the multiplication on F of H, which was again recalled as composition, then that induces a group structure on pi naught. And moreover, the index map, which takes a Freedom operator and assigns to it its index, is a bijection. Maybe I can just give a quick sketch of the idea here. So the part that it induces a group homomorphism and stuff, I would say that is just some formal verification and you can do it. But the fact that it is bijection is slightly more interesting. So if you are given a Freedom operator F, whose index is 0, you can check by some basic function analysis that there exists some G, which is an invertible operator on H, such that the difference between the norm of F and G is less than epsilon. And the point is that, yeah, so I would want to show injectivity. And to that end, I would want to show that if F is a Freedom operator with index 0, then it is connected to the identity, which is obviously a Freedom operator with index 0. That would be enough. And yeah, for that purpose, first of all, this thing follows from basic Hilbert space theory. And you also have another result which says that GL of H is part connected. In fact, a much stronger result is true that it is contractible, but we don't need that powerful a result for our purposes currently. GL of H is part connected, and since identity is also a Freedom operator, you can get that there exists some H in or maybe H is a bad letter, maybe L in GL of H such that, yeah, norm of L minus the identity is less than epsilon. And now the point is you can try and compose these three little parts using the fact that the space of Fredholm operators is open. So you have F, you have identity, you know it is open, so you have a ball like this, and you can get a invertible operator here. Here also you have an invertible operator, and they are locally convex, so you have parts like this, and now you can try and join these two parts by a part which you get from the fact that GLH is part connected. And yeah, the composition of these three parts will show that F is indeed connected to the identity, and this shows injectivity. Surjectivity is kind of just you take the shifting operator which takes EI to EI plus N for some given N, and you can check its index is minus N, and that will also prove surjectivity. So nice, we now completely understand what the part components of the space of Fredholm operators is. And the question is, we would try and generalize it in certain ways. Maybe two possible generalizations are possible. One is if we would try and compute the higher homotopy groups of the space of Fredholm operators, how do they look like? And the second one is this formulation where you can try and think of pi naught is nothing but the homotopy classes of maps from a point to your space of Fredholm operators. And on the other hand, it's an you can think of the integers in an extremely fancy way as the K group of a point. And if you consider the natural map, then the above proposition just said that this natural map is a group isomorphism. And we might wonder whether this thing can be generalized. And the answer is yes. The point is that if you have any compact Hausdorff space, then you have a natural isomorphism of abelian groups from the homotopy classes of maps from X to the space of Fredholm operators to the K group of X. And at this juncture, I want to make a remark which created a lot of confusion for me and some of my friends when we were first studying this paper, is that Atiyah mentions this theorem somewhere in the middle of the paper, and then he apparently doesn't mention its use or anything later on. And the point is the fact that it's an isomorphism has no use in the proof of Bott periodicity that he gives in the paper. All you need that is that you have a natural map from this homotopy class of maps to K of X. That is enough for the purposes of the paper. I will later show that if you have the additional data of that or the additional information that it is an isomorphism, then you can actually get much more nicer results. Okay, so this is precisely what I just said, that again, we just want the existence of a natural map from the space from the group XF to K of X. And it's the fact that it's an isomorphism is just a fact for us right now. It doesn't have much more consequences. And as a result, I wouldn't be going into the details of how you can prove Atiyah-Yanich theorem, but I will maybe just give an idea behind how this map comes by. And the intuition is kind of, again, note that associated to every Fredholm operator, you have two finite dimensional vector spaces, or the kernel and the co-kernel. And if you think about how K of X is defined, it's also kind of the formal difference of two, well, vector bundles in this case, but again, finite dimensional vector bundles. So you have a difference of things here, you have a difference of vector spaces of bundles here, and it is kind of tempting to sketch this argument that if you have two families of, yeah, so if you have such a map, you can try and define the kernel of this map by simply taking the kernel at every point. And similarly for the co-kernel, and these are indeed vector spaces, finite dimensional vector spaces, because the operators are Fredholm. And you might suspect that these two things, when you topologize it as a subspace of X cross H are vector bundles. But the sad part is that this does not always hold. And so this needs to be taken. I mean, you need to work something more in order to get this necessary map from XF to K of X. And to that end, we have a technical lemma, which says how you can salvage it. Namely, if you have a continuous map from X to F, and if you have a closed subspace V of your Hilbert space, which has finite codimension, I mean, there exists a closed subspace V of H, which has finite codimension, and which is always orthogonal to the kernel of each of these TXs for every X in X. And the good fact about this is that now if you take this collection of vector spaces, where you take your Hilbert space and you quotient by the image, which is nothing but the co-kernel of T of X, and this is finite dimensional because T of X is Fredholm. If you topologize it as a quotient space of X cross H, then this guy is a vector bundle. And this is something really nice, because now we will just take this bundle and take the difference with the trivial bundle, which is X cross H over V. So recall that V had finite codimension, so it also makes sense to take this quotient, and this is a legit trivial vector bundle which is of finite dimension. And finally, you have to take this difference. And the claim is that this is the map which Atiyah and construct, and yeah, it induces an isomorphism from this group to this group. But obviously, there are some checks which I am not going to do right now. For example, the fact that this is well defined up to, like, if you have two homotopic maps from X to F, these two things should give you the same result and stuff like that. But the point that I want to emphasize here is that the existence of this map is the most crucial part, because what follows next is just uses the existence and nothing more. Okay, so does anyone have any questions? Okay, if not, then let's move ahead and discuss a nice class of Fredholm operators, which are called Toplitz's operators. And actually, these are the players which are most relevant for Atiyah's proof of Bott periodicity. And again, my treatment here will be slightly different from what Atiyah does in his paper, in particular, the Wiener-Hopf operators and stuff. I mean, I think some of you mentioned that they were extremely complicated to read, and I also had the same feelings. So I never really went through them, but I came up with another way of discussing Toplitz's operators, which isn't very computational, and I think it's quite nice. Okay, so maybe a few definitions first. We take the Hilbert space H in the things that come to mean the space of L2 functions from S1 to C of n. And recall that this L2 space is, as a set, it consists of all those functions from S1 to Cn, such that the integral of the square of the norms is finite. And you can give it an inner product by simply integrating the inner product for every X over S1. This turns it into a Hilbert space. And this Hilbert space takes a nice action from the space of continuous functions on the circle, which takes values in n cross n matrices. And this is essentially, if you like, just a big generalization of a fact that the n cross n matrix acts on a vector in Cn and it produces another vector in Cn. It's just this thing, but done continuously for every point on S1. And the action, if you like, is called the multiplication operator. And the point, or like if you are from a function analysis background, you know that this is extremely crucial for representing your abelian C-star algebras in B of H and stuff like that. But the crucial thing that I want to mention is that these operators, which takes an element of L2 of S1 with values in Cn to the product of a matrix with this guy is a legit operator, and it has, in fact, it is a star homomorphism from the space of continuous functions on the circle with values in the matrices to the space of bounded linear operators on this L2 space. And now we want to somehow cook up with, or like come up with certain class of operators which only look at the positive part of our L2 space. But before we do that, we need some technicalities to resolve. So first of all, note that we have this isomorphism, which is extremely canonical. If you just think of Cn as a tuple of, or n copies of C, you can immediately get this isomorphism. And under this identification, our multiplication by F operator is going to be nothing but a matrix which takes this n many copies of L2 of S1 with values in C to, again, the direct sum of n copies of L2 of S1 with values in C. And the nice fact about boiling it down to the case where you only land in the complex numbers is that we have the Stone-Weierstrass theorem, which says that every complex polynomial, every complex valued function on a compact Hausdorff space can be approximated uniformly by okay, no, I think I just mean this particular version, that C of S1 is just the closure of the algebra generated by these polynomials, which I think you can also call the Weierstrass theorem. And in this regard, what we will be looking at is where you take only the polynomials which, or not polynomials, I mean, these are the polynomials. I mean, in the previous case, what I wanted to mention was you can also have negative indices k here. That was the Weierstrass theorem, because you need the algebra to be closed under complex conjugation. But if you just focus on the polynomials, which are again a nice class of, a nice subalgebra of the space of continuous functions, and if you take its closure, then this space is nice and it has a name. It is called the Hardy space, and we want to restrict our operator MF somehow to the Hardy spaces. And how you do it is you can write your L2 of S1C as H0 direct sum H0 perp. So recall that the orthogonal complement of H0 is going to be nothing but the span of Z to the n's where n is less than 0. And after doing this decomposition, and after suitably arranging the factors, you can get your operator MF in this form, where the top left corner represents how the mapping from one Hardy space to the other Hardy space looks like. And this is going to be the definition of a Toplitz's operator, which I associate with a matrix valued function on S1. So essentially what we are doing is we take this multiplication operator, which is very well understood, and we now brutally chop it down to the positive coordinates and see how it behaves therein. That is the essential idea. And the point is that this theorem is what we will need eventually, that if you have a map which takes, which is from the S1, the unit circle, to GL and C, then T of F is a Fredholm operator. So recall previously we were taking values in Mn of C, which had non-invertible matrices as well. Then we don't say much, but the point is if you land in the space of invertible matrices, then the associated Toplitz's operator is Fredholm. And yeah. Okay, maybe this remark is not very relevant right now. I changed a few things and I forgot to remove it. And let's quickly try and sketch a proof of it. The first thing is, well, this is some technicalities, which again, I think it will, I mean, I cannot make much sense of it while speaking, but the point is, if you take the inclusion and then you see how adjoint inclusion of a closed subspace into a Hilbert space would look like, you will immediately get that this J star J is going to be the identity operator on L2 of S1 with values in Cn, and JJ star is going to be the projection onto our subspace, the direct sum of the Hardy spaces. And in this setup, you can much more succinctly and cleanly write the Toplitz's operator associated to F as just J star MFJ, which I will leave you to verify. But this has some nice consequences once you write it in a very algebraically succinct form. First of all, we immediately get that the association of an operator F to the Toplitz's operator associated to it is a linear map, because the multiplication operators were linear. Second of all, note that the norm of the Toplitz's operator is less or equal to the norm of F, because if you take norm and use submultiplicativity of the norm and the fact that J and J star have norm 1, it follows. Also, you get that the adjoint of T of F is T of F star. And finally, it's kind of obvious that if you take the constant map 1, then it is going to be the identity operator, the associated Toplitz's operator. But the sad part is that this is not an algebra homomorphism, because you can check that Toplitz's operator associated to a product is not the product of the associated Toplitz's operators. And but we would somehow want to, we would somehow want to get to this result that if you have a element F in GL and C, then the associated Toplitz's operator is Fredholm. But to that end, we would be needing a lemma in order to bypass this non-equality of these two operators, which says that if you have element F, which is nothing but a loop in M and C, then this commutator is compact. And this is a technical lemma from function analysis, but this has a nice proof, which maybe I will just briefly say later. But once you have this lemma at hand, then we are kind of done. So for example, you can show that the difference of TFG and TFTG is going to be a compact operator. And to that end, if you just plug in the previous algebraic formulation of TF and just write it down, at some point you need to just plug in JJ star, because, well, this is a function analysis proof, and I don't think there exists any function analysis proof where you don't use the trick. So here's the trick of plugging in this JJ star and using the fact that J star J is the identity. Once you do that and you do the algebra, you will get it as a compact operator multiplied by certain things on the left and right. And since compact operators formed an ideal, this is also going to be compact. For the second part, which said that which essentially is the statement that we are trying to prove, we will straight up use Atkinson's theorem, because note that T1 minus TF inverse and T1 minus TF inverse TF, both of these are compact by the first part. So we are done once we recall that T of 1 was nothing but the identity. So Atkinson's theorem is also a very powerful result, and it comes very handy here. And finally, we get that index of TFG is going to be the sum of the indices of TF and TG, which you can just get by taking this difference and recalling that we had a result stated earlier that Fredholm operator plus a compact operator, this thing doesn't change the index. Okay, now the proof of this lemma I won't go into, but I would like to highlight this formulation of the Stone-Weierstrass theorem, which I kind of cooked up on my own. I didn't find it in any book, but I think this is quite handy. And maybe I just say what it states, that if you have a compact host of space, and if you want to kind of understand how or when a closed star subalgebra of matrix valued functions on X is equal to the entire algebra, and the technical conditions are that it has to contain all the elementary matrices and it has to separate points. This is the formulation of Stonemaster's, which I find quite handy in proving this lemma. And yeah, after that, the lemma is just some checks, which let me not go into. But the key takeaway from this discussion of Toplitz's operators is that we have this beautiful result, which is known as the Toplitz's index theorem, and it relates the degree of this map as, which is a very topological thing, right? You define degree as a certain map when you restrict to the homology and you see what it does on the homology, to the index of the associated Toplitz's operator. And yeah, the proof is kind of just using the things we have done before. So first of all, yeah, you note that if F and G are homotopic, then again, by the properties of invariance of index, this equality will follow. And if you have such a part, which, yeah, if you have such a homotopy, then you can just push everything forward with the aforementioned star homomorphisms I discussed, and they are continuous. And you will eventually hit, okay, there is a typo here. Yeah, you will eventually hit that both the index of TF0 and TF1 are the same. And finally, to note that the index is actually equal to negative of the degree of F. Note that we have this isomorphism, which comes from a very first course in homology theory, which essentially says that the degree of that any map F on the circle would be homotopic to a map of the form Z power n for some n, and this n is also going to be its degree. And using that fact, you can check that the homotopy class of F is same as the homotopy class of Z power degree of F. And now if we use the result of the invariance of the indices of the Toplitz's operators when your maps are homotopic, you will get that the index of TF is going to be index of TZ times the degree of F, because the degree of F will come out being a multiplication of Z degree of F times. And recall that we had the index of TFG is index of TF plus the index of TG. And finally, one little check is that the index of TZ is -1. That I leave to you. But the point is that essentially, if you, when n is equal to 1 and you are just mapping into the complex numbers or the units in the complex numbers, then this TZ is nothing but a right shift operator. And as I had discussed before, it has index -1. So nice, we have this nice result on the relating the degree of a map and the negative of the index of the associated Toplitz's operator. And now we have all the function analysis background required to present a proof of the Bott periodicity theorem. So yeah, first I want to define a nice class of, or a nice line bundle on S2, which I will just use this language clutched out of a map like this, because recall that one vector bundles on S2 essentially corresponded to homotopy classes of such maps. And in particular, if you take the inversion map and you consider line bundle you get corresponding to it, that is going to be my canonical line bundle. And then the complex Bott periodicity theorem is going to say that if you take the external tensor product of Kx and K of S2, where X is any compact Hausdorff space, you could take this map which maps into K of X cross S2, then this is an isomorphism, and moreover, the K group of S2 is nothing but the free abelian group generated by the trivial line bundle and the bot element, which I denote as, or which I define as H minus the canonic or minus the trivial line bundle. This is the famous bot periodicity theorem, and there are many equivalent formulations of it. In particular, you have this reduced version, which can be shown to be equivalent to the aforementioned version. And it says that if you look at the reduced picture, and if you multiply by the bot element B, then you get a map from K tilde X to K tilde X mash S2. And this is an isomorphism. And yeah, our reason or motivation behind developing this theory of top-list operators was that we want to come up with an inverse to this multiplication by the bot element map, which again we will just verify very little things in light of Atiyah's rotation trick, which is something which he mentions in almost all the papers he has written related to bot periodicity, in particular in the paper I am discussing, and also in the one where he uses differential operators and elliptic operators, stuff like that to do it. And the point is that the inverse to this map beta is essentially kind of characterized by three properties. Or in other words, if you find the map alpha, which is first of all natural, is Kx linear, where you put the natural Kx model structure on K of X cross S2, and which sends the bot class to 1 when X is a point, because then X mash S2 is going to be S2. Then this map alpha would induce a reduced version of the map from the reduced K group of X mash S2 to the reduced K group of X. And the claim is that this is going to be an inverse to the multiplication by the bot element map. Maybe before constructing such a map alpha, let me again highlight that this definition or this proposition nowhere mention any function analytic or any particular branch of mathematics kind of idea. And in particular, this kind of highlights why you have so many different proofs of complex bot periodicity. Many people come up with many different such maps alpha, and which do the job. For example, I guess the classical proof uses some things on Laurent polynomials and stuff like that, and that is such a map alpha. And this proposition essentially says that any such map alpha will lead to an inverse of this multiplication by the bot element map. So let me give you a sketch as to how you can construct this map alpha. It will be 5 steps. First of all, note that if you are given a vector bundle on X cross S2, then by some clutching construction, or maybe generalized clutching construction as is mentioned in some references online, you can get that this data is same as giving a vector bundle over X cross S1 together with a bundle automorphism of the corresponding pullback. I guess this picture immediately says why that is the case. If you believe that the vector bundles on the sphere is nothing but a vector bundle, is nothing but a homotopy class of maps from S1 to GLN. Okay, so this is the first reduction where we get a bundle automorphism, where we translate the data of a vector bundle on X cross S2 to the data of a bundle automorphism over X cross S1. And now the idea is that we are essentially looking at the home bundle, but then this home bundle is a natural bijection with section. We are looking at the homomorphism between these two bundles, and the point is that it is in natural bijection with the sections of the home bundle. This is some basic vector bundle theory, and moreover, you can check that in this correspondence, the subgroup or the group of automorphisms is going to correspond to sections wherein you land in the automorphism of each fiber. That's precisely what we do here, that if you take a map from X cross S1 into this aught of pi star E, then you can check that, I mean, by the definition of a section, you get a map which for every X in X and Z in S1 is going to land in the automorphisms of the corresponding fiber. But the fibers, you can continuously identify them with Cn. And therefore, this aught thing is going to be GLN. But there is again some technicality which Atiyah didn't mention, but I guess you need to pass to GL infinity, because while your vector bundle need not have that same rank throughout, I mean, you might have different part components and stuff. But once you push forward this thing to GL infinity, you get a map from X cross S1 to GL infinity. And this is kind of in similar spirit as to what we had seen earlier. I recall that we are somehow going to this functional analysis arena where we had a map from S1 to GLN, and we constructed this Toplitz's operator. And we want to get to that specific setup again. But first, a couple of things to note is that since X and S1 both are compact, then the product is also compact, and this map is going to factor through some GL and C. And moreover, since S1 is compact, you have that the map out of this product is same as a map from X to the continuous functions on S1 with values in GL and C. And now, if you recall our development of Toplitz's operators associated to any such map, we yielded a Toplitz's operator, and Toplitz's operators were Fredholm. So essentially, we have a map from X to the space of Fredholm operators. And finally, note that, again, the mere existence of a map from the homotopy classes of maps from X to F to the K group of X enables us to push forward this thing to K of X. And in this way, we have finally constructed a map which takes vector bundles on X cross S2 to K of X. And the claim is that this map is additive, and therefore, by the universal property, it yields a map from K of X cross S2 to K of X. And this is actually the map which is going to be the inverse to this multiplication by the bot element map. There are again some checks to do, which I am not doing right now, except for the fact that Atiyah's rotation tricks the last point, which required that when X is a point, this map alpha is going to send this bot element to 1. And that is indeed the case if you just use the fact that alpha is additive, and you use the fact that the degree of this map is -1, then you do get that alpha sends this class of H -1 to 1. And yeah, this was kind of a very brief idea of what Atiyah tried to do in this paper. And after that, maybe in the next couple of minutes, I just briefly say what the homotopy groups of the space of Fredholm operators look like. But for this calculation, you need the full power of the Atiyah-Janich theorem. Namely, you need to know that not only do you have a natural map, you also have an isomorphism. And why do you need this? Well, the point is, if you investigate the map that I had discussed before, then you can check that that map restricts to a map from this pointed space y0 to this pair of spaces F and F0, where F0 denotes the space of Fredholm operators with index 0. And you can check that this map restricts to a map from this homotopy classes of maps to the reduced K group of Y, where of course Y is a pointed space with base point y0. And now if we assume the star is an isomorphism, then this map is also going to be an isomorphism. And the technical lemma is that what we are trying to hit is that a formulation of the reduced K group of a pointed space in terms of a homotopy class of maps from X to some nice subclass of Fredholm operators. And to do that, I have a technical lemma here, which let me not discuss right now, but the corollary is that the reduced K group of Y is same as the pointed homotopy classes of maps from Y naught to the space of Fredholm operators, where you fix point the identity. And now we are kind of done, because if you plug in Sn on both the sides, on the one hand, you have the reduced K group of Sn. On the other hand, you have the nth homotopy group of F, where the base point is the identity. But note that all the potential you have two different group structures, they are the same by an Ekman-Hilton argument. And now by Bott periodicity, you know the reduced K groups of Sn, and therefore you also know all the homotopy groups of F, which are Z if n is even and 0 otherwise. And yeah, and maybe you might be wondering, I mean, why focus only on the component of identity? Why not anything else? To that end, I have another result from Hatcher, which says that, yeah, so the point is that every part component of F has the same homotopy type as F naught, and the reason being that F is associative H space whose multiplication induces a group structure on its components, and you can show then all the part components are indeed homotopic. So yeah, I guess that's all I had to say today. Thank you.
Okay, let's thank Anupam for the great talk.